Good morning, everyone. Alright, I've got this all set up. We're going to have some videos today that we'll have as part of the class. But we're going to go ahead and start chapter 4 now. So this will be a kind of material that's not going to be on this exam, but it'll be on exam 2. Which is really focused on electrons and how the periodic table works. So in the last chapter we talked kind of about the nuclei, we talked about protons, neutrons, we talked about charge and mass number and atomic mass and moles and all this fun stuff. But we kind of we mentioned electrons and we talked about their charge and how they can contribute to the charge of an overall atom if they leave or come in. And so we're going to see that the chemistry that we deal with is mostly about the movement of electrons. And so we're going to see that we're going to have an entire chapter just on electrons here. So it'll be fun. This chapter is pretty conceptual. There's going to be a couple things that may be a little bit more difficult. They may take a little more time to process. But, it's not that bad. Don't worry. And this one, there's not too much math in it. So some of you will appreciate that. So this will be a kind of a change of pace from talking about all these empirical formulas and moles and things, and now we're going to be talking about how electrons absorb light and how we can talk about different electrons within an atom and kind of their relative energies. So often though we kind of like to start talking about the periodic table, then talk about electrons, and then talk about the periodic table again. And so it's an interesting way of teaching it. And so let's just take a look at the periodic table. Some basic terminology we have. So, if you take a periodic table, looks in this general form, right? There's a couple of terms that we should know so that when we are talking about the periodic table, we are all on the same page. So, we're going to see that these columns in the periodic table are called groups, and the rows are called the period. So on the top of them, oftentimes you'll see, most people actually just say 1 and 2 for these. So the first column is group 1, the second one is group 2. We skip kind of over that middle section. Oftentimes you'll see this one now as 3A, 4A, 5A, 6A, 7A, 8A. Or sometimes you'll see this as 13, 14, 15, 16, 17, 18. Either one's okay. They're pretty common. And then here you just get all these 3Bs and craziness happening here. In fact, sometimes some will start with 7B or 8B, and then 3B will actually be a little bit further in this thing. So we don't have to worry about that. We're going to mostly focus on those kind of higher up ones in this course. And the periodic table is kind of designed, at least historically, such that things in the same column or group, as we call it, behave similarly. So we see that everything in group 1 tends to react the same. They tend to have similar properties. Everything in group 7 or 7A, 17 or 7A behaves the same as everything in that column. And to illustrate this, we've got some fun videos. Let me just pop one open here. These are from our textbook, in fact. So let's see here. Should be on the first page. Yeah, that's the video I'm looking for. All right, let me go ahead and switch windows here. In this video, I'm going to mute it. I've got lithium, sodium, and potassium chunks. These are all in group 1 on the periodic table. And we're going to see what happens. We see all of these, by the way. They look essentially the same. Silvery metals, metallic substances. I'm going to dunk all of these things into water. I don't know if I do anything. Oh yeah, I just show you how easy they are to cut, but who cares? Let's watch them go in water. So here's the lithium. Lithium reacts with water. We can see that it's fizzing and bubbling, and you know, there's some steam coming out there from all the heat that's being released. And it just kind of does its thing. And does its thing. It's pretty cool. Watch it kind of go crazy. Notice also it's really light. Lithium, even though it's a metal, floats on water. In fact, all of these metals float on water because they're not very dense. Sodium, now, let's go ahead and see what's going to happen with that. We see it's kind of a bit more vigorous here, right? It kind of is zipping around. It's kind of formed this like layer on the outside of itself. This is pretty interesting because it doesn't want to be with the water, but it's reacting with it. And so, let's see, is it going to pop? I don't remember if this one does. This is always an interesting thing, a demonstration to do in class, because sometimes it like explodes really violently, and sometimes, oh, there we go. And then here's potassium. And hopefully we can see this one is quite a bit more reactive, right? That was pretty cool. Let's just watch that again. I think it's super cool because you get this purple fire out of it. And we'll talk about why that fire is purple. But isn't that cool? And there it goes. So potassium, far more kind of reactive than sodium. And then the lithium is the least reactive. If we just hop over to the periodic table real quick. No, go away. If we look on our periodic table, oh, I'm sorry. We are still on this. Okay, sorry. If we look at the periodic table here, with all my things blocking it. Okay, hold on, let me move our chat box, maybe. Yeah, okay. So we can see here, lithium, sodium, potassium, are all in the same group of the periodic table. So they have similar behaviors. They all reacted with water. They were all kind of less dense with water. And when we talk about chemical reactions later on in the semester, we'll see that they will behave pretty much identically. And we're going to see later on that electronically, I mean, in terms of their electrons, they have similar, what we call configurations. And that's going to lead to these properties. So that's just a little example of what we mean by their behave similarly. So those elements within the same group had similar reactive capabilities. So they all reacted with water. They theoretically would all burn. You know, they produce fire because it's such a, you know, energetic process. So they're very happy to react. Should be noted, by the way. No, we'll talk about that later. Okay, so let's talk about some of these groups. Some of these groups have special names that we're going to want to learn. We're going to see group 1. That's going to be lithium, sodium, potassium, etc. We call the alkali metals. This is excluding hydrogen. Hydrogen we don't call an alkali metal because hydrogen is not a metal, right? We know it's a gas typically, and hydrogen actually kind of deserves its own category. It's its own element. So, but this will be basically like lithium, sodium, potassium, rubidium, and cesium and francium. So again, they're all right here in that leftmost column. Again, don't bother memorizing these by any means, but that's the group that we're talking about. So those are called alkali metals. Group 2 are called the alkaline earth metals. And that would be like magnesium, beryllium, calcium, strontium, barium, radium. So those are going to be our group 2 ones. We'll see that they are somewhat similar to the alkali metals, but they're a little less reactive. And we'll talk about why later on. And but they're kind of similar. Hopping over the groups now, we're going to go all the way to the end. We're going to talk about group 18 or 8A, the one on the very far right. So now we did this one. This was the alkali metals. This is alkaline earth. Now we're going to hop all the way over to 18. If my arrow will draw. No, it won't. Okay, well, whatever. These are what are called noble gases. These ones all happen to be gases that don't react. And in chemistry, noble means not reactive. So they just don't react. And so they're called noble. You probably have heard about noble metals as well, like platinum, gold. Those are called noble because, not because they're expensive, but kind of, because they don't react. So gold and platinum are valuable because they don't react very easily. Silver does react, right? We know it tarnishes pretty easily. We'll talk about that corrosion process later in chapter 10 or so. So those are our noble gases. If we now move a little bit left, these are now the halogens. That's going to be fluorine, chlorine, bromine, iodine. Oh, what's the next one? Astatine? I don't even know. Yeah. Because acetatine's radioactive, we don't really use it. So halogens are, their name means salt forming. The alkali and alkaline earth ones, by the way, those names come because when you react them with water, they produce a basic solution. We'll talk about acids and bases at the very end of the semester, but that's where that name comes from. So, you know, when you hear about like alkaline water, for example, that has it's a little more basic than regular neutral water, and so that's the same name there. So alkali, alkaline earth, it comes from the fact that they produce bases when in water. Noble gases we just talked about, they don't react, they're gases. Not to say that gases don't react. Gases certainly can react, but these ones don't. The halogens, two of which are gases, are very reactive by comparison. We know chlorine, for example, is very toxic. Bromine is also incredibly toxic. Iodine can be, but we also use iodine. You know, it's a necessary nutrient for us. We use it to kind of sterilize things, or at least sanitize things. So like if you get a wound, you put iodine on it to clean it. Fluorine we need for our teeth. Chlorine is a very important ion in biology, so all these things are important. Those are halogens. Their name means salt forming. So, you know, for example, sodium chloride has chlorine in it. That's the element Cl. That's an example of a halogen, so something that makes salt. All right, and the last one that we have a special name for are called the chalcogens. Except I can't spell chalcogens. This is a less common name. If anything, learn those first four. This one is a little bit less common. Nobody really says the chalcogens, but everybody says the halogens and alkali metals and all that. So, but this will be like oxygen and sulfur and selenium and what else is even there? I don't even know. Tellurium maybe? Whatever. Those are chalcogens. Their name means chalk forming. So or kind of like rock forming. So that's kind of the other group that has a fun name. So that's going to be the kind of elements, the columns that have special names we're going to see. Further on the periodic table, we can make some more kind of distinctions. Today I'm going to be drawing a lot of these. Whoops. We're going to see we can kind of talk about sections of the periodic table. If I kind of make some distinctions here, anything that's in this is called a main group element. Same thing over here. These are also main group elements. So the things that have those kind of higher groups, the ones that we're talking about, groups 1, 2, 13, 14, 15, 16, 17, 18, those are all main group elements. Main group elements. Same thing. So we can kind of just classify those. So those are the elements we're going to deal with most commonly in our work here in chemistry. In the middle, we have the transition metals. They're going to have very different behavior, but transition metals are actually pretty similar to each other. So they all have their own, like, kind of, I don't want to say personalities, but they kind of have personalities, you know, in patterns of behavior. Chemical behavior, that is. And then finally at the end here we have what are called the inner transition metals. And this kind of chunk is often put at the bottom. The reason for that is to save space. If we were to really include it in the periodic table, our periodic table would look like this. Too high. So this inner transition metal portion is kind of, that's where it would go on the periodic table. Like you would have our first two columns, then we'd stick that chunk of just 2 rows with 14 elements, and then we'd have our transition metals, and then finally the rest of the periodic table. But as you can imagine, that would just take a lot of space, and so oftentimes we kind of just take this bit out and just stick it on the bottom like this. But we'll see here that if we were to put it together, it would look like this. And if you look at some of the, we can see here also with the periodic table things in a period increase by atomic number. So like boron is atomic number 5, carbon is 6, nitrogen is 7, oxygen is 8, and we keep on going on. If we kind of see here, see cesium in the 6th row here is 55, barium is 56, and then we hop down to lanthanum in those inner transition metals, and we go all the way to lutetium, 71, and then now we go back to hafnium. So on this periodic table, in fact, they have kind of that little space here for where the inner transition metals would go, right here. And so that's where those would happen. Okay, but let's not worry about those quite yet. All right, so we can describe any element by talking about its atomic number, right? We can also identify where it is on the periodic table. We can say, okay, what is the halogen in period 4? We can do that, for example. Let's do that. What element is a halogen in the 4th period of the periodic table? What element is a halogen in the 4th row? Let's look. So we're looking for a halogen. Halogens are group 17 on this particular periodic table. Again, some of them say 7A, but we're looking at here. We're looking at the 4th row So helium's the first row, then neon, argon, krypton. So we're looking in this row here of the periodic table, the fourth one down, and we're looking at the halogens. So the answer for this particular question is bromine. That would be the element that we're looking for. So we would go ahead and look at the periodic table. Halogen tells us this is group 17 or 7A, and period 4 is the fourth row. And so we have Br here. Or if you want to give your answer, you could say bromine. Elements, by the way, are generally not capitalized. So like if you say bromine, typically it's all lowercase, but the abbreviation Br has to have a capital B and a lowercase r. So those are kind of important distinctions that you'll talk about, that are more important next chapter, in chapter 5. So, but might as well just tell you that now. So you can find an element on the periodic table. Not that difficult. What else can we talk about? Ah, yes. Some general properties. We're going to see, what's after silicon here? Arsenic? Yeah. We see often, if we look at a periodic table, they kind of put a kind of step ladder kind of thing here. That generally surrounds these elements like silicon and arsenic and boron. We're going to see that by and large, most elements on the periodic table, I'll make that even bigger, are metals. These are also metals down here. In transition metals, right? Alkali metals, alkaline earthy metals, transition metals, right? These are all metals. We'll talk about what metallic properties mean. Over here we have non-metals, things that are not metal, not metallic, and then kind of things along that green line are best described as semi-metals. So they're kind of not quite metals, not quite non-metals, they're in between, or we might describe them as metalloids. So kind of somewhat metals. And different periodic tables have different kind of ways of describing them. On this particular periodic table, it looks like the semi-metals are in this kind of reddish underline. So it's generally that kind of staircase down. I'm not going to be like super crazy about the metalloids, because some periodic tables do them a little bit differently. And so I want us to focus on what are definitely non-metals and what are definitely metals. So that's the more kind of big one for us. But two very important metalloids, though, are silicon and germanium. Those are super important. Silicon is incredibly useful for our computer chips, right? That is a huge driving force behind technologies, the element silicon and some of the properties it has. And it's because it's a metalloid, same with germanium, that we're able to do such interesting things with it, because it kind of has its own unique set of properties. A lot of the metals behave the same. Like if you have copper wire versus silver wire versus gold wire in your house, probably you have copper because who the hell has gold wire, but they all conduct electricity really well. You could have iron wire, you could have chromium wire, all of those conduct electricity really well. Silver is actually, by the way, the most conductive element there is. So if you are extraordinarily rich, you can have silver wires and conduct things slightly faster than with copper. But have fun with that. We're going to see the nonmetals are a bit more varied in their properties, but the metals tend to be essentially very similar to each other. Okay, let's talk about what we mean by these things. What are metals? How do we know something's a metal? How do I know that... How do I not have a metal here? Oh, I do. How do I know that this thing is metal? I mean, we can identify it as that, right? We know it's got metallic properties. What are some of those? Well, pretty much all metals except for one are silvery in color. The one element that isn't is copper, of course. The rest are pretty much all silver colored, by and large. These also tend to be pretty hard. Excuse me, or dense. We know iron, for example, is a pretty tough material. It's heavy for its size, so it's dense. Sorry. My ring actually is made of tungsten, one of the most dense elements. Second densest, I think. I think iridium has a higher density. Let's see, what else do we have? Metals are shiny, which is what we call lustrous. Metals are often, let's see, what else can we say about metals? They typically are conductive to both electricity and heat. So we'll talk about why that is in chapter 6, I think. They are typically malleable, meaning you can work with them to change their shape pretty easily. Like you can make thin sheets of metals pretty easily. If you tried to hammer out a non-metal, you'll see it will just shatter rather than kind of change its shape pretty easily and still stick together. We can see these are often pretty ductile as well. Ductility means the ability to kind of make a wire out of it, so you can stretch it out. You can kind of pull it out and make wires out of it that'll stick together. Like if you try to do these with non-metals, you're going to just break them. What else do we know about metals? That's a pretty good start, at least for their kind of physical properties. If we look at non-metals, they are going to be either colorful or colorless, depending on what you're looking at. Carbon, for example, is black. Sulfur is yellow. Bromine is kind of reddish-brown. Chlorine is greenish-yellow. Oxygen is blue. They all have just, and phosphorus, white, red, coming in a couple different allomorphs, but these typically are colorful, or they're colorless. Like helium is colorless, hydrogen is colorless, xenon, all the noble gases are colorless. So, oh, I know another one. These are typically solid. So metals are typically solid, right? Typically have high melting points. Non-metals are typically gases, but there are, of course, some that are solid, some that are liquid. There is one liquid metal that's mercury. Super interesting metal, by the way, but also quite toxic, so we don't really play with mercury anymore. Let's see. Often non-metals are soft or brittle. So they are easily kind of squishy. You can squish some phosphorus. It'll probably explode, but you can squish it. They're brittle like charcoal. If you take a piece of charcoal and hit it with a hammer, that's carbon, by the way, it's just going to bust into a million little pieces, right? Little grains. It's brittle. Often metals or non-metals are dull, so they're not shiny. We don't think of charcoal as something shiny. or reflective. Sulfur is this dull yellow solid. These are non-conductive, so we do not make wires out of phosphorus, for example. Doesn't make sense, or sulfur. They're also non-malleable. They're brittle. They just break. And then finally they're found in all states of matter. And most are gases. So nitrogen, oxygen, fluorine, chlorine, all the noble gases, those are all gases at room temperature. A couple of them are solid, like carbon, sulfur, phosphorus, selenium, and then we have bromine, which is a liquid. So we have kind of one liquid in each category, but nonmetals can typically have all sorts of different states of matter. So just some general characteristics. We're going to see later on that most metals will form positive ions. I'm using this in a different color because now we're talking about chemical properties. And we're going to see later on that most nonmetals will form negative ions. Remember, ions are charged atoms, so they will gain or lose electrons to change their charge. We're going to see often metals will form positive ions and nonmetals will form negative ones. But that's going to come a little bit after with this. All right? So, cool. So those are just some characteristics of metals and nonmetals. We see again, by the way, most of the periodic table, most elements by far are metals. We have like, what, 15 nonmetals and 100 metals, so, and a couple of metalloids, I suppose, but by and large, most elements are metals, and they typically have these characteristics. All right. So there's some lists of facts, I suppose. Let's talk about now. That's kind of some trends in the periodic table that we have. Similar properties within things. We saw some things in the group behave similarly. Generally, metals all have similar properties. Non-metals have similar properties. We're going to see why these are in kind of our exploration of electronic structure of atoms. And we're going to kind of begin that by talking about what electrons do within an atom. And then we'll talk about how they're organized. So kind of just how do electrons behave? And in order to kind of answer this question, we're going to go ahead and, for right now, we're going to use our kind of Bohr model of the atom, where we have our nucleus and we have our kind of orbits. Remember, this is called the Bohr model. I'm not going to ask you that, but suffice it to say, this is a just a way of describing atoms. One very important kind of property of electrons, if I kind of describe this ring as, say, I'll just call it ring number 1, n equals 1, so ring number 1. And I could say this ring is ring number 2. One very important property of electrons is if we zap them with light, they get excited. Light is a form of energy, right? We'll talk about light in just a little bit here. But if I give an electron some energy in the form of light, electrons get excited. This one we can call a ground state. Ground state atom. It's got its electron. I guess this is a hydrogen atom. It's only got one electron. It has its kind of electrons at its lowest energy. We'll see some terms here. It's kind of the lowest energy level. And we can excite it by giving it some light. If we do that, let's redraw our atom. Now we'll see our electron has jumped into our second ring. We call this an excited state atom because it has more energy. It's excited. We've given that electron some energy, and it's jumped up into a higher orbital. Just like how matter cannot be created or destroyed, energy can't either. So what happens is the electron has absorbed the energy. It absorbed that energy and now has gone into a higher energy state. You've given it more energy, so now it has more energy. And so now it is zipping around in the excited state. And now what's interesting, so let's see. We gave it its energy and it kind of jumped up, right? After a while, perhaps a nanosecond or two later, these can be very fast processes, we might say, okay, it's going to kind of relax now. It's going to now go back to its energy level, and it's going to spit out that light. This is, again, light energy. It's going to be spat back out. And now we are back to our ground state. We're now back in our ground state. So it's now back to its low energy level. So we call this, it's releasing the energy. And we call this relaxation. So this is excitation. And this is relaxation. So we've given it the extra energy. It's super hyper. It's crazy. And then it releases that energy back out. And then it's back to its normal ground state. So you'll see, like, what the hell's the point? It absorbed the energy, then released it. That's the end. Here's the important part. We're going to see that the energy of the photon, we call it, of the light, we call this a photon. A photon is just a unit of light. Like we say an atom is a unit of matter, a photon is a unit of light. It's kind of just a light with a specific energy, is the same going in and out. What I mean by that is we're going to talk about light in just a second. We're going to talk about how white light has a couple of properties that can correlate with its energy. So how much energy a specific beam of light has. And what's very important here is the light that's going in, that's being absorbed by an electron, is exactly the same energy as the light that's coming out. And that specific energy is very often unique to a particular element. We're going to see that elements can only absorb and release very specific energies of light. So the energies of light that a sodium atom absorbs are very different than one a copper atom absorbs, or a calcium atom, or a potassium atom. Each element has its own kind of set of which energies of light it can absorb. And that's going to be very, very important for us, because it gives us, as you'll see if you ever take analytical chemistry, it sets the foundation for us to be able to identify elements very easily. By just shining a bunch of light at them and seeing what energies they absorb, we can identify it. Yes, correct, it's only transferred. So we can give energy to something and then it comes out in another form or the same form. Like we take in chemical energy, we give out heat energy or mechanical energy. With these, it's going to be both light energy for both. So they'll absorb a specific energy of light, they're going to spit out a specific energy of light, and that's going to be kind of their own thing. So they just hold on to it and then they release it. Okay. Cool. What this means is that for, let's say this is a hydrogen atom, it turns out for this atom, we saw that we moved from level 1 to level 2 with this particular kind of excitation pathway. We're going to see in atoms there are infinity different levels. I mean, there's kind of a limit, but theoretically there's no limit. But because at some point it just leaves. It's gone so far away from the nucleus that it just leaves the atom. But what's important here is because a very specific energy of light is needed to go between the kind of lower energy and the higher energy circle in our model there, in our atom, that the energy of light, excuse me, the energy of light needed is what we call quantized. And again, that means that it's very specific, there we go, very specific. So quantized means it's got to have like kind of the same energy. So if a I'm just going to make up some numbers. Let's say for this excitation to happen, I'm just going to give us a number that is totally made up and it's completely not even close. But let's say that a light beam comes in to both of these. And let's say that this first light beam has an energy of 10.02641 times 10 to the negative 19th joules. Whatever, I'm making this number up. This is how specific these are, by the way. And let's say this one is 10.429 times 10 to the negative 19 joules. So tiny amounts. It's just one photon of energy. It's not very much. But we're going to see that this atom perhaps it will absorb that first one, but the second one it can't absorb. That's the idea here. That's how specific these are. Electrons will only absorb exact energies very, very specific energies of light. And that energy corresponds to the energy difference in the levels. We see that the difference in energy level for this atom, from going from n equals 1 to n equals 2, from the first one to the second ring, would be equal to that difference there. And again, these are totally made up numbers, so this is, I mean, don't remember these numbers, but the point is the energy that it absorbed of the light is equal to the energy difference between those two levels. The farther you go from the nucleus, the higher energy you are, because electrons, being negatively charged, like to be as close as possible to the positive nucleus. So the farther out you go, the higher energy you are. And we see that there are very specific amounts of energy that are required to go from each level to the next one. And so it's important because, as a result, electrons will only absorb very specific bits of light here. Let's see this in action. What's the point, right? Let's see what the point is. So if we go back to this here, I didn't click it. Oh wait, hold on, I've logged out apparently. 1 second. I do this, and we'll look at another video. This is one of my favorite ones to do in class. It's nice we can finally actually start bringing in some of the videos now. Okay, so let's see here. Where are we? Talk about light in a second here. Aha! So, flame tests. An old way to detect certain elements. We have more specific ways now. But if we just look at this mesmerizing fire, we see we have the fire of different colors here. We have green fire, red fire, purple fire, and I guess that one's like kind of orange. Well, we'll see as we move it around. These are different elements that are being burned. Yeah, there we go. There's our kind of orange. Just needed a little shake. There's some green. And then that one's going to be kind of more kind of purplish pinkish. I don't know if you can kind of tell that from this video, but here, let's watch that again. There are different elements in there that are being excited. We're giving them some energy, and they are releasing energy of very specific colors. This is how fireworks get their colors. That one on the right is either strontium or lithium. Then we have sodium. Sodium is, again, that orangey yellow, normal fire color. That's copper there, giving us the green. And then the last one, I think, is potassium, which gives us that purple. I don't know if you remember the previous video, we had the purple potassium exploding. That's why the potassium is purple, because it can only very specifically give out those colors. And while we haven't really talked about light quite yet, we can see that each element has its own kind of colors that it absorbs and releases. So we see potassium has got that purple, sodium gives that yellow orangey color, lithium is a red, strontium is red. They all have a kind of different energies here. And so not only is it just pretty, but it's very useful for talking about identifying elements. So very useful way to identify elements. All right, let's talk about light then. So light. Important here because we're talking about how light and electrons interact. Light is a wave, right? It's technically a electromagnetic wave. That means it has an electric field and a magnetic field that are perpendicular to each other. We don't need to worry about that. Just suffice to say they're waves. And waves have certain characteristics that I'm very bad at drawing, but Gosh, my allergies. It's September. Why am I still having allergies? We have some things we can talk about with these. The difference here, the length of these is what's called wavelength. And that's the difference between kind of the top of one section of the wave as it's oscillating. It just goes up and down. And, I mean, I'm terrible at drawing, but ideally these are equally distant. So they have a very specific wavelength. That's what we can talk about. We also see that they have something called frequency. That's the Greek letter nu, by the way. It looks like a V, but it's a fancy V. Here, I'll try and draw it again. So it's just a fancy V, Greek letter nu. Frequency is just kind of how quickly that is moving up and down. In frequency, we might think of, like RPM, like in your engine. Your RPM, your rotations per minute, is a frequency. It's how often something is happening, how many times it's rotating per minute. We're going to see with light, it's how often it's going up and down, so how quickly it takes for it to complete one cycle. So how quickly it's going from the top of one portion of the wave to the next top of the portion of the wave. And we're going to see that these two are very important for us to talk about. One other one is the speed of light. That's a constant. You don't need to memorize it, but it is 3.0 times 10 to... Is it 3.01? No, I think just 3.0 times 10 to the 8th meters per second. Not a number you need to memorize by any means, but that's how quickly light is moving. So light moves from point A to point B extremely quickly. And it has these other two properties, the wavelength, the frequency, as well as the amplitude. We can talk about that. And this is related to kind of the intensity of the light. We're going to see that the wavelength and frequency determine kind of the color of the light or the type of the light or how much energy it has. The amplitude is how intense that light is. So, I mean, you've all been driving, and then there's those cars that have these extremely intense lights, right, that we all hate, and it's just blinding us in our rear view mirror, right? They're the worst. But that's intensity, so how kind of bright it is. The wavelength and frequency talk about how the energy of that light is, and how kind of what color it might be, or what have you. That's what the wavelength and frequency. These talk about the energy of the light. The amplitude is really the frequency. I'm sorry, the intensity of the light. How intense that light is. Alrighty, so let's talk about these. We can talk about the energy of light, of specific photons. We look at one wave of light at a time. That's a photon. We see that it's a spectrum. We see that we kind of have a lower energy side of things and a high energy side of things. And we can say maybe, I don't know, right here, this tiny little bit here, we always bring this out, we have visible light. And visible light, we're going to see, has also specific... we're going to see that some light is higher energy than other lights. Oh, I forgot purple, didn't I? And I'm totally out of space. Okay, hold on, let's fix this. We can pretend... Yeah, we're going to move it right there. Put blue back. And then we'll put our purple. Okay, there we go. So there's our rainbow. Rainbow is part of the spectrum of light. But we're going to see that if we talk about wavelengths, our kind of visible range, things that we can see, are between our wavelengths of light, so that the kind of peak to peak distance of the light waves fall between 400 to 700 nanometers. So nanometers, we should probably remember, is just below micrometers, right? Microns. Micrometers are kind of the next big unit, and then we have millimeters, like 1,000 micrometers is a millimeter, right? So these are really short. And we're going to see that we can only see things that fall between this range. So we have a very kind of limited field of vision. A lot of other animals, while they cannot, detect as many colors as we can, actually can see quite a bit more into what's called the ultraviolet region, so a little bit less than 400. And some animals actually can see more colors than we can. We can see essentially anything that's, red, green, and blue in any combination of those. Those are the kind of color receptors we have in our eyes. Like there's some shrimp that have 12 different color receptors. We have 3. We can kind of see 3 different colors and then extrapolate the rest. But like mantis shrimp can see 12 different colors and then every combination of those. So it's quite remarkable. Anyways, biology aside, we see here that if we kind of go towards the higher energy side, we get ultraviolet light. That's going to kind of be our next section of this. And that can go down to maybe about 100 nanometers or so, roughly speaking. And ultraviolet light, we know, is higher energy, right? We go out into the sun and we get burned by UV light. And we're going to see that that's higher energy light than visible light is. And so, as a result, this kind of ultraviolet light is higher energy. It's capable of making electrons jump farther and farther up their orbitals. That's where the problems come, right? That's where, when you start, well, UV light can't do this, but never mind. We'll talk about X-rays and talk about that. So below that, if we go shorter than UV light, we get into the X-ray range of things, going down to, let's say, I don't know, maybe about 0.1. Yeah, we can go even smaller. So maybe picometer range. So between 10 picometers and 100 nanometers is X-rays. X-rays, as we know, are even higher energy. We don't want X-rays to be zapped at us, right? Those are what are called ionizing radiation. The energy is enough that it actually kicks electrons out of atoms and forms ions. Because the energy is so high, it gives electrons so much energy that they completely jump so far away from the nucleus they just leave the atom. And so those are particularly dangerous. If we keep going, we get gamma rays. I'm going to write them down here. And those are the highest energy we have. Gamma rays are in space, really. We don't really see those on Earth. Those are extremely high energy. They're deflected away by the Earth's magnetic field. We don't have to deal with them, but those are even higher. So those will just destroy things. So super high energies are gamma rays. Sometimes called cosmic rays as well. So high energy ones are down there. Notice, by the way, the wavelength for all these gets smaller and smaller. So we see that energy and wavelength are inversely proportional, right? So as wavelength goes down, as our waves get shorter and shorter, their energy goes up. And we'll see a little bit about that in a bit. So if we want to kind of keep talking about things, if we now maybe start talking about higher or lower energy, higher wavelength, on the other side we have infrared here. Infrared light we can detect. We can't see it per se, but we have it. We can detect it kind of as heat. We feel infrared light. We can't see it, but we can feel it, and that's these are technologies used by, like, you know, in the old days it was used by printers, remote controls. They use infrared light to carry signals, and these go to about 10 micrometers or so. Is where the kind of infrared light kind of leads us, and we kind of have then microwaves after that. So microwaves actually have much lower energy than you might think. You know, like you put something in a microwave, it gets all hot, you might think you're giving it a lot of energy. Microwaves, I mean, you are, because you're doing tons of microwaves on them, but that's you're giving them kinetic energy. The rest of the micrometer kind of stuff here goes, that's where we're going to have our microwaves, and then after that we have radio waves. So radio waves are going to go from kilometers. You know, they have kilometers between their tops of their waves. So huge difference, right? Picometers to kilometers. Like, it's incredible. We see that microwaves, so infrared light is kind of capable of making things vibrate. It can't really move the electrons anymore, but the atoms can vibrate more frequently with infrared light. With microwaves, they can't even vibrate, they can just rotate more. And that's how your microwave heats up your food, by the way. It rotates water molecules. It causes water molecules to rotate, and then the friction of water molecules rotating into each other causes them to heat up. It's just kind of, as they rub against each other, they give off energy, and that energy is as heat. So, and then radio waves is just not even, you can't really do much with those. But that's where, like, your Wi-Fi is, where your cell phones are operating, radios, television, all operate in the radio wave kind of area. And again, we see here that the wavelength of the light is the opposite of the energy. They're inversely proportional. In fact, we can put them in terms of a formula if we like. You don't need to use this formula in this class. You'll use it in C101 if you take that. But these two are constants. They're just numbers. Planck's constant is 6.626 times 10 to the negative 34. Here, we can do it. Joules times seconds. And then we also know that, again, this is not something you'll need to know. That's Planck's constant. That's h. And c, we saw, is 3 times 10 to the 8th meters per second. Over your wavelength will give you your energy. Note the units, by the way. We just have conversion factors. Seconds will cancel out. Lambda, the wavelength, would be given in meters, so that would cancel out. And we'll be left with joules. Joules is a unit of energy. So that's how we can relate them together. But the point is, though, from this formula, what you should be able to identify is that as wavelength goes up, energy goes down. That's the point. And if we want to talk about frequency instead, we can do that. The frequency is the speed of light over the wavelength. So we see it's the same idea. As your wavelength goes up, your frequency goes down. This should be a little more obvious though, because frequency is how quickly, time-wise, it's able to get from the peak of the wave to the next peak of the wave. And all light moves at the speed of light, so we're going to see that because it's all moving at the same speed, the shorter distance it has to go, the more frequently it's going to get there, right? The shorter amount of time it takes to go between them. So it's all about how quickly it's going to take the light to move between each wave, or each crest of the wave. And since we see these two are together, we're going to see that as frequency goes up, energy goes up. They're directly proportional. So, because they're both the opposite of wavelength. We can also frame energy in terms of frequency. As one goes up, the other goes up. Hi, buddy. Okay. Exciting. So we're not going to need to use these equations, but this is what I want you to know from this. These are the important relationships between wavelength, energy, and frequency. Those are the important bits here. I don't need you to learn these constants. I don't even want you to use these equations. I want you to understand the relationships between wavelength, energy, and frequency. And we'll see. So very specific wavelengths of light can be absorbed. Very specific colors of light can be absorbed. The wavelength tells us the type of energy that we're dealing with. So we saw that the copper gave out green light. It's only absorbing something that maybe is 502.714 nanometers in length. And so that's the idea here. So we say very specific wavelengths or energies of light. Those terms are interchangeable because we can convert between wavelength and energy. But I think that's enough of that. So if you can understand the kind of ideas of this, that's what I want you to kind of work with. Okay, so I want you to understand those relationships. Alright. The last thing I want to talk about today is how wavelengths interact, or how waves interact. We're going to see that light is a wave, right? We're going to see electrons somewhat act as waves sometimes, and we're going to see why that's important next time. But we're going to see that light waves can kind of interact together. And if you remember back to math class, maybe you've talked about this sort of thing before. I hope those are kind of in line with each other. Let's pretend they are. You can add waves together. And we're going to see that if they're kind of all in phase with each other, which I tried to do, notice that, say, the peak of this part is exactly aligned with the peak of this part, which clearly it's not, but pretend it is. If they were aligned, oh my gosh, they should also have aligned with this bottom one. Here, let's try that again. Okay, we got this, guys. We can do it. Okay. Okay, let's pretend. Ideally, this would all line up. Essentially, if they're completely in phase with each other, that means that their peaks line up, their troughs line up, they have the same wavelength, all that good stuff. They would just add to each other, and they would completely make just a bigger amplitude wave, a more intense wave of light. And we're going to see that if they're the opposite of each other, and we try and add them up, we get nothing at all. If we try and put these two waves together. This is how noise-canceling headphones work, by the way. They don't use light waves, they use sound waves, but they take information about sound waves coming in and they make the completely opposite sound wave and they broadcast that to you, and the waves will cancel out and you will not hear anything. And so it's interesting technology. This is called destructive interference. And this is called constructive interference. And so we kind of put it where we're talking about where these will constructively perfectly interfere with each other, where they will be exactly in phase, and then where they're exactly out of phase with each other. And so those are kind of the extremes. Constructive, they completely add together exactly, and now you've got one of double amplitude, double intensity. Or where you had them completely cancel each other out and you have no intensity at the end, no amplitude. And so there are other ones, like if they're half phase, half not, we'll have one that has half the energy of or half the intensity of the other one. And so it's just kind of an array. And we see that we're going to talk about this in terms of electrons as well. So we're going to see electrons that do exhibit some wave-like behavior. They can also constructively and destructively interfere. And we're going to adapt our kind of Bohr model with those orbits around to incorporate this idea of how they're behaving as waves. And we're going to see there are certain areas where electrons will always destructively interfere, meaning they will not be able to exist there because they'll cancel each other out. And we're going to see areas where electrons will be able to kind of definitely go, and that'll be the more constructive side of things. And so we'll see that electrons exhibit this behavior too. But that will be next time. So, all right, with this, I have a couple of announcements. Tomorrow, Friday, what day is that? 17? We're going to have a review, because I was asked to do that. We'll have it on Discord. How that's going to work is, it's quite simple. I can, in fact, show us. Let's see. Let me go here. So, I'm going to change windows here. So tomorrow we're going to have a review. I can do that before every exam, that's okay. How this works, I'm going to put I'm going to have a review questions channel so y'all can you can put questions there. How it's going to work is tomorrow at 9, Friday at 9, for people who are watching this later. Again, I'm going to let y'all know about this. I'll put out an email. All you have to do is click this little classroom bit. Now you'll be able to hear me. We'll just do it here because you can ask them questions verbally. Might be a little easier on you. And what I'll do is I'll show my screen as well. So I'll say whatever I'm broadcasting Discord. You'll see this live button by my name. And you'll just need to click that twice. Double click it and then you'll be able to see my screen. But then you can also talk with me. If you want, you can mute yourself. I've just done that. You can deafen yourself, which is, I don't see why you'd ever do that. because deafening makes you not able to hear. But so if I just say that's it, I'm broadcasting Discord right now, so you're just watching an infinity mirror, which is pretty interesting. But that's how that's going to work. So tomorrow 9 o'clock. If there are questions, if you guys want to do this, put some questions here, put screenshots, or say like, hey, can we do an empirical formula problem again? And I can spell again properly, I swear. Or you can just post a screenshot of a question from one of the worksheets, like, I really didn't get this one, or hey, I'm struggling on this one. Can we go over it? So pictures are great. General things like this, I can try and answer. Some of these, like empirical formula, I have to plan ahead because I need to have the numbers ready. I can't just make up numbers for those. So it is helpful if you kind of put questions in this for me to go over. Or if you want, you can just talk. And we'll see how far we get. So that'll be between 9 and 10 tomorrow. All right? So, heading back here. So that'll be between 9 and 10 tomorrow. I'll record it. So it won't be on Twitch, but it will be on our YouTube channel. It'll be on YouTube later for people who can't make it. So if you have questions and you can't make it, put the questions there, write them out, and then we can go over. If nobody writes questions, though, and nobody shows up, then obviously I'll just leave, right? So it's for y'all. So if nobody has questions, then I have nothing to do there. So it'll be posted to YouTube later. It won't be on Twitch because it's harder for me to get to hear you guys as well as broadcast without weird things happening. So so it's just going to be easier if we do it on Discord. So, all right. So we'll do that tomorrow. Have fun studying on your exam. Just remember there are practice exams. I do have some of those way at the bottom of Canvas. So I would definitely take a look at those. Your exam, again, is multiple choice. It's going to be on Canvas. It'll be on Monday. There will be a 24-hour window of time for you to take it. And so you'll go from there. All right? Cool. In that case, we'll end for today. And maybe I'll see you tomorrow, maybe not, depending on what you'd like to do. So, alrighty. Awesome. Take care then. Enjoy the rest of your day. Happy studying.